In this video, we're going to take a look at finding critical regions for a Poisson distribution. Now let's just start here by quickly recapping the definition of the critical region. So the critical region is the range of values of the test statistic that would lead to you rejecting H0, our null hypothesis. And the value of values on the boundary of the critical region are what we call the critical value or critical values. And for further stats 1, you need to be able to find the critical region for both one and two-tailed tests. So let's just have a look at this then in a little bit more detail. So let's just start off then with one-tailed hypothesis test. So for one-tailed hypothesis test here, well, we have two possible options for the alternative hypothesis. Remember, the alternative hypothesis is H1. And just recall from the previous video then, this will be either, so we've got H1 here for lambda is strictly greater than m, or we have H1 for lambda is strictly less than m. And this is dependent on the context of the question. Okay. Now, given that we have a one-tailed hypothesis test, there is a single part to the critical region and therefore only one critical value. So that's one-tailed test. What about now two-tailed tests? Well, for a two-tailed test, this has a single option for the alternative hypothesis. So a little bit more straightforward then. We simply have for H1 here, lambda is not equal to some value m. Now, for a two-tailed hypothesis test then, there are two parts to the critical region and therefore two critical values. Okay, so hopefully the material that we've just briefly looked at here is relatively straightforward. This is largely just a recap of A-level material, but now applied to further stats 1 for the Poisson distribution. Okay, but there we have it. So that's everything that we need then for our introduction here. Let's take a look now at some practice questions. So let's start off then with question 1 here. So for question 1, we're told that a single observation is taken from a Poisson distribution with parameter lambda, and it is desired to test lambda equals a against lambda being not equal to a using a 10% level of significance. So for the first part of this question then, all we want to do here is find the critical region for this test. So for part A then, where we want to find the critical region for this test, let's just start by writing down the hypotheses here. So we've already been given them. I just like to start by writing these down myself. So we've got H0 and H1. So for H0 here, this is lambda equals 8. And then for H1 here, our alternative hypothesis, this is for lambda being not equal to 8. Okay, so lambda is not equal to 8 there. And we're using a 10% level of significance. So the first thing that we do here is we assume that H0 is true. Okay. So we assume H0 is true. And the reason that we do this is because we now have our random variable here. Let's call this x. So we've got the random variable x here, which will follow a Poisson distribution with parameter lambda. However, if H0 is true, our parameter here would be equal to 8. Okay. So the parameter then, lambda is 8, like so. And like we said then, we have a 10% level of significance. Now, for this hypothesis here, this hypothesis test, we have a two-tailed test. Okay, so we need to half the level of significance here. Okay, because we have two tails for our distribution. So 10% split into 2. So we split this in 2. That would give us 5% in each tail. Okay, so 5% each tail. So what we require here then is actually two things. We're going to think about this in two parts. So we've got the lower tail of the distribution, and we also have the upper tail of the distribution. So let's start with the lower tail then. So for the lower tail then, what do we require? So for the lower tail here, we require that the probability of our random variable x here, so the probability of our random variable x here is less than or equal to some value. Let's call this c. And this must be less than our significance level here. And this isn't 10%. Remember, we split this into 2. So this would be 5% because it's 5% in each tail. Okay, so this is for the lower tail. This must be less than 0.05. Okay. So to find this now, all we need to do is either use the tables in the back of our formula book or just use your calculator. Okay. Either way, you should get the same thing here. So what I would get then is the probability that x is less than or equal to 4. So this here then is equal to 0.0996. So 0.0996 here. And clearly this is greater than 0.05. Okay, so that's greater than 0.05. So that does not satisfy this condition here. So we keep going. Now clearly this would decrease now. So it's going to be x less than or equal to 3. So we need the probability of that. Like so. And again, just use the tables here. Just do it using your calculator. Either way, you should get 0.0424. So 0.0424. And clearly this time now, this probability here is less than 0.05. Okay. So therefore, what we found here now is the critical region for the lower tail. So lower tail critical region. In this case then would be x less than or equal to 3. Okay. That's x less than or equal to 3. So that's the lower tail. We now need to consider the upper tail. So for the upper tail then, we'll do that over here on the right. Okay, and this is still part of part A here. So we're not done yet with part A. So for the upper tail then, this time now we require the probability then. So the probability that our random variable x here is greater than or equal. So greater than or equal to some value, let's call that C again. And this must be less than, again, our significance level here of 5%. Okay, so less than 0.05. Okay, so again, you can do this either using your tables or just use your calculator. But either way, you should get the same as me here. So we have the probability then that x is greater than or equal to 13. Okay, so this would be equal then to 1 minus the probability that x is less than or equal to 12. Okay, so this is equal then to 1 minus 0.9362. And this here gives me 0.0638. And clearly this is greater than 0.05. Okay, so this doesn't satisfy this condition here. So we need to keep going. So in this case then, this would now increase. So it's going to be x greater than or equal to 14. So the probability then that x is greater than or equal to 14. So in this case then, this would be 1 minus the probability that x is less than or equal to 13. Less than or equal to 13. And in this case, then we get 1 minus here, 0.9658. So 0.9658. And if we evaluate this here, this gives us 0.0342. Okay. And clearly this probability here is now less than 0.05 as we require them. Okay. So less than 0.05. So therefore what this means then is we have now found the upper tail critical region. So upper tail critical region. So the upper tail critical region. This would be given as x being greater than or equal to 14. Okay, so x is greater than or equal to 14. So now for the actual critical region for this test, we just need to put both of these together then. So therefore, critical region for this test. So the critical region for this test here this would be given as, so we've got x being less or equal to 3. Or we have x being greater than or equal to 14. Okay, and there we have it. So that's the solution to part A. Like you can see, the two-tailed hypothesis test, as we can see here in part A, There is a little bit more work involved because obviously we need to account for both tails, but the method I'm working hopefully shouldn't be too challenging there. Okay, so that's the solution to part A. So let's just box this off then. Now for part B, this is actually pretty straightforward. So for the actual significance level of the above test then, so let me just write this down. So for the actual significance level here, this would simply be equal then to, so it would be the probability that x is less than or equal to 3. So probably that x is less than or equal to 3 plus the probability then that x is greater than or equal to 14. Okay, so it's the sum of these two respective probabilities. So x is greater than or equal to 14. So in that case then, what do we have? Well, I've got 0.0424. So 0.0424 plus, so the probability that x is greater than or equal to 14, that's 0.0342. So 0.0342 there. Add those together then, what we get here is 0.0766. Okay, and there we have it. So that gives the solution there to question 1. So let's just take a look then at one more question here to finish with. So we have question 2, and it's known that an estate agent sells houses at a rate of 10 per month. The estate agent believes that the rate will decrease for the next month. So for the first part of this question, then part A, it asks us to find the critical region of a test at the 5% level of significance to determine whether the rate of sales has decreased from 10. So for part A then, let's just write this down here. We're looking for the critical region. So to start with here, I'm going to define the hypotheses. We've got H0 and H1. So we have H0 and H1. So clearly we're looking at the mean of a Poisson distribution here. So our parameter would be lambda. So I've got lambda and lambda. Now for H0, the null hypothesis, we're looking at whether the mean here, or our parameter lambda, is equal to some value, which in this case, that value would be 10, right? We're looking at whether the rate of sales has decreased from 10. Okay, so lambda equals 10. That gives us the null hypothesis. And then for the alternative hypothesis here, H1, well, if we're looking at whether the rate of sales here has decreased, and decreased is the key word here, then H1 will be for lambda being strictly less than 10. Okay, so that's the first part complete. Now what I need to do here is assume that H0 is true, because we want to start here with our random variable. So if we assume that H0 is true, so we assume that H0 is true, like so. Then in this case, if H0 is true, if we have our random variable, let's call this x, which will follow a Poisson distribution then with parameter here, well, if H0 is true, our parameter then would be 10 because lambda equals 10. Okay, so our parameter there is 10. And what we require now is the probability. So the probability then that our random variable x here is less than or equal to some value. Let's call that c. And this here, this probability must be less than the significance level of 5%. So this must be less than 0.05 here. Okay, so all we need to do now is either use the tables at the back of your formula book or just use your calculator. Either's fine. Usually people find it a little bit easier to use the tables, but if you prefer the calculator, that's absolutely fine. So in this case then, we will get the probability that x is less than or equal to 5. Now this here would be equal then to 0.0671, so 0.0671. Now this value here is greater than 0.05. So that's greater than 0.05. So this doesn't satisfy this condition here, so we need to keep going. Now clearly this value must get smaller. So now we look at the probability then that x is less than or equal. So less than or equal to 4. And if you evaluate this here, this gives us 0.0293. Okay. Now this probability here is less than 0.05. So that's strictly less than 0.05 here. And therefore that satisfies this condition here. So we find the value of C then. And what that tells us then is we have now found the critical region. So in that case then, so therefore the critical region is, in this case then, x is less than or equal to 4. Okay. So x is less than or equal to 4 there. Okay. And there we have it. So that gives the solution to part A. So let's just box this off here ever so slightly. Like so. Now for part B then, it just asks us to find the actual significance level of the above test. So this is actually pretty straightforward because the actual significance level is just equal then to this probability here. So let me just write this down. So the actual significance level is equal then to the probability that x is less than or equal to 4. Okay, which we've already evaluated. That was 0.0293. So that's equal then to 0.0293. Okay, and there we have it. So nice and straightforward. That gives the solution to part B. And that gives us the solution there to the very last question, question 2. And that brings the end of this video on finding critical regions for a Poisson distribution.